All right, guys, for those of you tuning in, I'm going to get started shortly. Just kind of let you guys figure out, click the link, get here, get going. I'm just going to be mainly going over those 4 problems at the back of your gas law review checklist, and then a couple other tougher problems that we did in class, but I just wanted to take our time here, 'cause sometimes we get a little bit rushed in class, and maybe I was going too fast, you couldn't keep up, bell rings, gets a little hectic, you know the deal. So I'm going to go over a few of these just a bit slower, just kind of go over kind of strategy when it comes to solving these types of problems, because usually the hard part is figuring out where to start. Where do I start with a problem like this? And then as soon as you figure that part out, it gets a bit easier. So if you're just tuning in, like I said, I'm going to wait a minute or so just to let people kind of work their way in here, get their computer, get somewhere quiet, somewhere where they can think. If you can't get anywhere right now, or you click this link by accident, you just realize you don't have the time to tune in, I'm going to send out the link to this from my YouTube channel, and you can watch it anytime, preferably for third block before tomorrow, third block, because that's your test, and for fourth block on Tuesday. But anyway, the first question here, especially in third block, raised a little bit of confusion, and I think it's a lot easier than it first appeared. And I think it led to confusion because you were making assumptions about the rate of the other gas. So the problem says, what is the rate of a fusion for a gas that has a molar mass twice that of a gas that effuses at a rate of 3.62 moles per minute? So notice that it doesn't say that it's 3.62 times faster. It doesn't say that. That is a no. It says that it effuses at that rate. So you know that the lighter gas, because it says that you're trying to figure out what the effusion rate is for the gas that's twice as heavy. So you know that the lighter gas is effusing at a rate of 3.62 moles per minute, which means the other rate is not 1. The other rate is what you're solving for, which is X. But let's take a step back and see how we set this up in class, and we can see how this actually gets to be a bit easier. A lot of us in class set it up as 3.62 equals the square root of 2x over x. And we set x to be the molar mass because we don't know the mass of the lighter gas, and we also don't know the mass of the heavier gas, but we know that it's twice as much as the lighter gas. And what you'll notice here is that those x's just cancel out. They go away. Regardless what the weight is of the lighter gas, if the heavier gas is twice as big, then the heavier gas, when you do that division, is always going to end up being 2. If the lighter gas is 1, the heavier gas weighs 2. That's twice as big. 2 divided by 1 is 2. If the lighter gas weighs 5, the heavier gas weighs 10. 10 divided by 5 is 2. The lighter gas weighs 100. The heavier gas weighs 200. Again, you divide those numbers, you get 2. So even though you have technically 3 variables, you don't know the weight of the lighter gas, you don't know the weight of the heavier gas, and you don't know the rate of the heavier gas. One of those variables, or 2 of those variables I should say, that is the weight of the heavier gas, are not important because when you put them into the Graham's law equation and do that division, you're always going to get the square root of 2 on the right-hand side because it's always going to be twice as big. Therefore, when you divide them, you're always going to get 2. So in reality, this side of the equation under the square root is always just going to be 2, which means we're just solving for the rate of the heavier gas and that is our only variable. So first thing you do is just figure out what the square root of 2 is, which is like 1.4 or something. So we get, I'm just going to put this off to the side, 3.62 over x equals 1.41. Now I'm just going to put that over 1 just to make the cross multiplying a bit easier to see. Cross multiply, you'll get 3.62 equals 1.41x, and you'll divide each side by 1.41, and 3.62 divided by 1.41 is 2.57 moles per minute. And now here comes the last part of our kind of test strategy here, problem-solving strategy in general. You got to ask yourself, does this answer make sense? Did I get an answer that predictably makes sense? And I would say yes, because if the rate of the lighter gas is 3.62, you know that the rate of the heavier gas has to be smaller than 3.62, because kind of common sense, but we also talked about it in class. Heavier gases move slower. Lighter gases move faster. So we got an answer that's less than 3.62, so reasonably we should say that we are correct. Can you predict in your head the exact answer? No, but at least you can predict the trend where the problem is getting you to go. If the pressure goes up, the volume's going to go down. When you solve for a problem that has a pressure increase that's solving for volume, your correct answer should be a volume decrease. So if you get an answer where V also went up as pressure went up, there's a good chance that you got it wrong. All right, someone asked, and feel free to text me on Remind as you're doing this, why did you put 3.62 over x? So I'm just going to erase this just so I have room again. So why did I do 3.62 over x? So if we go back to our original setup, 3.62 is the rate of the lighter gas. And strategy-wise, it's always smart to put the rate of the lighter gas in your numerator. The rate of your heavier gas is what you're solving for. That is your true unknown. And we set that equal to just radical 2, because since the other gas is twice as heavy, that means every single time when we do the division over here, we get 2. Because when you set up that right-hand side equation, if you do light over heavy on the left side, you have to do heavy over light on the right side. It's like a little inverse there. You flipped it left and right. So I put the lighter rate in the numerator here, which puts the heavier rate in the denominator here. And then on the right side, since it's heavy divided by light, that's always going to be 2. Do you have to do it that way? Nope. You could have also done x over 3.62 equals radical 0.5, because then you would be doing heavy divided by light on the left side, which is going to be light divided by heavy on the right. And in that instance, it's not going to be radical 2 anymore. It's going to be radical 0.5, because the heavier gas is twice as big as the lighter, and that's going to be 1 over 2. Hopefully that clarified some things. All right, next one. From here on out, these kind of tougher short answer questions, you're probably going to be using the Pivnert equation for pretty much every single one. All right, so I don't remember if I mentioned this to my third block, but I changed millimeters of mercury to kPa just to make the problem kind of possible. I think in years past, I gave you the conversion for millimeters of mercury. And if you see a question like this on a test, there would be another conversion there given to you just to make sure that you were good to go. This is a Pivnert problem. You have grams, you have liters, that's volume, you have temperature, grams you can convert to moles, which is N, R is a known constant, that you need to memorize that's been given to you on that front sheet. So start memorizing that. And you're solving for pressure. So the first thing you gotta do is change 1.09 grams of H2 to moles. And to do that, to get N, just take the mass given to you in the problem and divide it by the periodic mass of whatever the gas is given. In this case, it's H2. H weighs 1. If you have two H's, they'll weigh 2. You do 1.9 divided by 2. To make this easier, let's just assume that's 0.5. It's pretty darn close to 0.5, so let's pretend. Your temperature, you got to convert to Kelvin, 273 to that. You'll get 293. And then from here, it's just a little bit of setup and a little bit of algebra. Pressure is your unknown. You have volume. You have moles. R, if your pressure unit is kPa, is going to be 8.314 times 293. Divide both sides by 2. And just multiply and divide over there on the right. And you will get, in this case, 609. I think in class, when we didn't round this number to 0.5, we got like 660, something like that. But I rounded to 0.5 just to move along quicker. That's pretty basic PivNert, little two-step PivNert problem. You need moles. The conditions were not changing. It didn't say the volume increased from 2 to this. It didn't say the temperature decreased from 20 to blank. Or there was no conditions being manipulated at all. You just have a gas. You're in a container. What's the information about it? PivNert. All right, the first thoughtful problem has a couple of ways to solve it. Both will involve partial pressure. One way will be solving it using like that partial pressure formula where you have to do a mole fraction times the total pressure. That gives you your partial pressure of whatever gas you're talking about. And that way is less setup, more algebra, or you can PivNert it twice, which is more setup, but less algebra. Usually what I'd recommend is doing whatever way is comfortable. I'm going to PivNert it first because PivNert is kind of universal for this whole unit, so you can pretty much PivNert anything. And let's see how you would go about doing that. So you have a 1.42 gram sample of helium. I know right off the bat, I'm not going to read the rest of the question. I'm giving grams. I'm just going to convert that to moles right now. So for your N, you are given 1.42. Helium has a periodic weight of 4, and that was given to you in the problem. So your N for helium is 0.355. Room temperature is Celsius, but I mean, you could look that up. On a test, I would make sure to give it to you. The partial pressure of helium is 42.5. The partial pressure of oxygen is 158. What is the mass of the oxygen? So if you do decide to go the PivNert route, and I made sure to clarify this in class, you do not know what R is for torr. So if I remember correctly, I gave you these values for helium and oxygen in terms of atmospheres. So helium in terms of atmospheres, instead of 42.5, would be let's just say 0.056 ATMs. And oxygen would be 158 divided by 760, 0.207 atmospheres. And I definitely remember giving those values in ATMs in class. So our temperature needs to be in Kelvin. We would add 273 to that. So that in Kelvin is 298. And if you're going to PivNert this, you'll notice that you don't know the volume. So you have to get the volume of the flask And you can get that from PivNerding with helium. And then once you get the volume, you can PivNerd it again for oxygen, then get the moles for oxygen, and then you can convert that to grams. So, after one PivNerd, you have the pressure of helium times your unknown V equals the moles of helium, which is 0.355, times the R for atmospheres is 0.0821, and we are at 298 Kelvin. Divide both sides by 0.056, and do a whole lot of work in the calculator. Hear your wife laugh at you because she gave you a calculator that jams on like every single button.
Maybe get your own calculator.
And you'll get a volume of 155 liters. So that's the volume of your container. That's the volume of your flask, which was not given to you at the beginning of the problem. So now you can use that volume and PivNerd it again for oxygen, because now you have all the information for oxygen except for N. You do not know the oxygen's N because you don't know oxygen's mass, because that's the question. The question is trying to get you to solve what is the mass of oxygen. So you're going to end up PivNerding it again and get, Marge says hi.
Hey, Marge.
She said,
pick a name. That's all I'm going to say.
What is she for you?
She's Margaret in my class.
I don't know. She's not going to pick a name. So we're going to take that V and we're going to plug that in and PivNerd it for oxygen. What? The volume is 155, Maggie. So we got our V was 155. Now we can plug in that V for oxygen and solve for N. So oxygen's pressure was 0.207, 55. That's the volume. The N for oxygen, Trin says hi. You don't know. The R is 0.0821. And the temperature is not changing. That's still 298. Divide by 0.0821 times 298 on both sides. Divide by 0.0821 times 298 over here. Plug that into your calculator. That's going to make a lot of noise because it jams on like half the keys. Don't laugh. This is
grateful.
And you'll get an N of 1.31 moles. And you know oxygen weighs 32 grams per 1 mole. Look at that dimensional analysis. Moles cancel, and you get 42 grams. So that's how you do it, PivNerding it twice. You PivNerded it once to get the volume from helium's information. You PivNerded it again to get the moles of your oxygen, and then you multiply that by the mass of oxygen, because we all know, based on the periodic table, how much 1 mole weighs. Predict your answer. You have more than 1 mole. Therefore, your answer should weigh more than 1 mole. So 1 mole weighs 32. We got an answer that weighs more than 32. There's a decent chance we're right, or at least on the right track. So that's how you do it. Maddie wants me to say hi to the dog. Hi, Harper. She's just staring at me. She's probably wondering who I'm talking to. Not you, Harper. I'm talking to my students. Except right now. Now I'm talking to you. All right. How do you do it the partial pressure way? I'm assuming whoever just texted me means you got 1.33 moles. That's fine. That's not your final answer because it wants it in grams. So the partial pressure way is a bit more of a pain in the butt, but doable. You don't have to worry about converting anything pressure unit-wise. The temperature is not going to matter. But the partial pressure way is, you know that helium's partial pressure, so that 42.5 from helium, is equal to the moles of helium divided by the total, so let me put moles of He, divided by the total moles times the total pressure. So we know the total pressure because you can just add 42.5 and 158. And that should be like 200.5 or something like that. 200.5. What are you laughing at?
I just think you're funny.
Because I remember solving this like 2 days ago? Yep, hilarious. The moles of helium we just did before, but since I forgot what that was, let me put that in again. That was 0.355. So, we just got to get the total moles because we don't know what that is. And once we have the total moles, we can then get the moles of oxygen from this formula again, and then get the grams of oxygen. So, this one's less setup, but sometimes people really goof on this algebra. So I usually divide by 200.5 first, both sides, and then it's just cross-multiplying and dividing. Some people like to start off with like crazy cross-multiplying, and then they get confused with what happened over here with this 200.5, and then they end up just doing something funky, and then they're wrong. So we're going to avoid that by just not doing that. So 0.212, put that over 1, is 0.355 over x. You'll cross-multiply and divide. You'll end up doing 0.355 divided by 0.212. And you will get x is equal to 1.67 moles. That is your total moles. That is the oxygen and the helium added together. So now we need to figure out what are the moles of just my oxygen. Well, you're going to do the same thing and use the same equation, except use oxygen and not helium. So, oxygen's partial pressure was 158. You don't know how many moles of oxygen you have, but you know that the total moles is now 1.67. Multiply that by the total pressure, which was 200.5. And you're going to do the same kind of thing again. You're going to divide each side by 200.5 and cross-multiply and divide. So divide each side by 200.5. And if you want from here, even before you do the 158 divided by 200.5, you can leave it like that and then just straight cross-multiply and divide from there. Doesn't really matter. Either way, when you perform this cross-multiplication and division, you should get an x equal to let me see here. So 158 divided by 200.5 is 0.788 times that by 1.67 and 0.32 moles. That is of oxygen. Multiply that by the weight of oxygen, which is 32, and you again get 42 grams. Hey, same problem, done two different ways. All right, let's see. I got a bunch of text on my mind. Is there going to be a problem this hard on the test? I don't know. You're doing a great job. Thanks. Okay, 10 out of 10. Love it. I got 1.33. You're good. Say hi to your dog. I did. Question about the castle learning. Let me answer this really quick. The earliest one. I wouldn't say this question was hard. It's just a lot of work. Yeah. I don't think this was that hard. All right. Next one on this page was the humidifier one. You know I don't like doing a lot of work. I like simple. Take Regents? I don't know what you want me to say to that. Anyway, a humidifier's water vapor flowing throughout a room. Job is to keep water vapor flowing throughout a room. A humidifier is used in a bedroom kept at 22 degrees C. The bedroom's volume is 4 times 10 to the 4th liters. Assume that the air is originally dry and no moisture leaves the room while the humidifier is operating. If the humidifier has a capacity of 11.6 liters of water, will there be enough to saturate the room with water vapor? So this one was like really thoughtful. Not so much math involved in this one at all. This one was just like super thoughtful. The question's basically asking, is there enough water in this humidifier to fill the entire room with water at this temperature? So the first thing that you needed to do was figure out how much water can fit in that room at that temperature. And there is a nice, lovely graph on the reference table that shows a relationship with vapor things at pressure, and that's table H. I should have a reference table in here somewhere. Boom. So if you go to table H, table H is the vapor pressure of 4 liquids, one of which is water. So you can figure out some information about water at that temperature given, which was 22 degrees Celsius. Most importantly is you can figure out the vapor pressure. So at 22 degrees C, and you might need to make a little bit of an estimation here, it hits, so that line right there is 20. So it hits right about here, let's say, which for simplicity's sake, if you have a reference table out, I'm going to say that's about 2. That the pressure of that water vapor at 22 degrees C is 2. So you need to figure out how much water vapor is created to get you to 2 kPas of pressure. Because this unit on this graph is in kPa. So we need to figure out how much water vapor exists at 22 degrees Celsius at that pressure in the volume of the room that you're given. So let's go back to the problem. So we're not really at this part of the problem yet. We're not concerned with the 11.6 liters. We're just trying to figure out how much water vapor exists in this bedroom at 22 degrees Celsius. So we said that, and to figure that out is a good old Pivnert equation again. So we said that at that temperature, you're at a pressure of 2. The bedroom is 4 times 10 to the 4th liters in volume. You're trying to figure out how much water exists at that pressure, volume, temperature condition. So we don't know how much water is in this room yet. We just know how much pressure it's putting down on you, the vapor pressure. R is 8.314 for kPa. And then convert 22 degrees Celsius to Kelvin, which should be 273 plus 22 is 295. 295 Kelvin. So you're solving for N again. So just divide both sides by 8.314 times 295, and you should get an N of 2 times 40,000 divided by 8.314 divided by 295. You get an N of 32.6 moles. Yeah, you have to get table H. You're going to get, if you do the Castle Learning, you will get questions that just directly say you need to use table H. You can't have table H memorized. It's way too complicated. So we have 32.6 moles of water in our room, which if we convert it to grams, water weighs 18 You get that from the periodic table. It's H2O. You get 587 grams of water is what the humidifier needs to pump out into this bedroom to keep it saturated with water. The humidifier has a capacity of 11.6 liters, which is 1,100 milliliters. And since the density of water is 1 gram per milliliter, that's also 11,600 grams. So there's 11,600 grams of water in your machine. Your room needs 587 to be saturated, aka completely filled with water. So yes, your humidifier can do this quite easily. It sounds like you have a pretty big humidifier. So if I were you, I would use this humidifier to saturate a much larger room with water vapor and not your tiny bedroom, because it is doing work. Okay, let's see. Questions on Remind. So table H, again, you'll get. You don't have to memorize that. That'd be crazy. This is a weird question. Kind of. It's a thoughtful question. You have to think about it. Part of it was like, do you know what a humidifier is? Which, I mean, I defined for you in it. So the left side of the equation, I mean, you can convert this number out of scientific notation. There's a question about the scientific notation. I don't know if I quite understand it, but if it was a question about how to put that in your calculator, and you don't have a scientific calculator and you're using one of the blue ones, one of the skills you learned in the skills unit was converting numbers into and out of scientific notation. So that 4 times 10 to the 4th is 4 with the decimal moved over 4 times, which is 40,000. I think that's what you were trying to ask. The question seemed a little simple when you first asked it, but I think you were trying to say, how do I convert this out of scientific notation if I am given a basic calculator that doesn't have exponents? In which case, you learn that skill not only this year, but in many other science classes, and math 5 through 8.
Yeah.
When do they learn scientific notation, Mrs. G?
I mean, they definitely do it in 6 and 7.
Or they should. Maybe we should say they should be doing it in 6th and 7th grade.
Yeah, it should be 6, 7, 8.
Yeah. In math.
Just doing it with a 7th grader or an 8th grader in math this week, so.
Yeah, tutor it up. A student of mine confirms 5th grade is when you learn scientific notation. So
Go student.
Go student. Thank you for remembering. Okay, I don't know how much more I'm going to do because I didn't want to make this too long, but keep texting away with your questions. Okay, and I will go back as soon as I can. If you think I'm going too fast because of the algebra, I am not going to show all my work with the algebra. I think setting it up is the hard part. If you get it wrong because of your algebra, you're losing significantly less points than getting it wrong because you're not setting it up at all. So just keep that in mind. Ooh, middle school was a rough time for me. I don't know if I can remember that far back. Middle school is kind of rough for everyone, is it not?
Yeah.
Yeah.
The definition.
But you know what? I remember a lot from middle school. You should turn on YouTube comments. Absolutely not. YouTube is the site of like Troll Central, and I'm not turning on comments on YouTube. Not a chance. I can watch my very niche drum videos teaching me drum lessons, and there's trolls on there being jerk faces. So there's no way in the world I'm ever turning on YouTube comments. It's just not happening.
People are nice in my comments.
I'm just saying that YouTube community in general is not nice.
I'm just saying.
And
You
I
shouldn't underestimate people.
do you even have your comments turned on?
I do have my comments turned on.
They can text me on Remind like they're doing now. I'm not even going to check those comments anyway. Now I'm getting derailed. I've been accused of stereotyping, perhaps. Do we need to know atomic structure for the test? No. I decided not to put that on there because I don't really want to squeeze too much unnecessary topics onto one test when we can just save that for later. Plus, I think you'll find out that most of that unit's pretty easy. There's like one really weird topic in atomic structure, so I think you'll be okay. 5% remaining means I gotta go ahead and do this problem, or just plug my iPad in. Anyway, the vapor pressure of water at 25 degrees Celsius is 0.0313 atmospheres. If 1.5 grams of water is enclosed in a 2-liter container, will any liquid be present? If so, what mass of liquid? So, you're given a whole lot of information, and you have to remember when you're using these equations that these are gas equations that give you information about this substance as a gas and not as a liquid. So when you read this and say, nothing's changing, I'm going to PivNert it, which would be correct, the answer you're getting is telling you how much water you have, not how much liquid water you have. So keep that in mind. Basically what's happening here is you have a container, it's closed, you have 1.5 grams at 25 plus 273 is 298? 298, yeah. At 298 Kelvin. And what's going to happen is some of that 1.5 gram liquid is going to evaporate into, this is a question that was in, this was not a question that was on your stapled checklist. This is just another question that I'm just going over. That was part of another sheet that you have. Anyway, some of that's going to turn into a gas. At any given temperature, substances are turning into gases. It does not matter if it's at its boiling point. That substance can still evaporate. Puddles of water disappear outdoors, even though outside it will never be 100 degrees Celsius, or else you would be in big trouble. Evaporation can occur at any temperature. So at this temperature, you're trying to figure out, as I drop my stylus, how much of that liquid has turned into a gas, which basically means you're trying to figure out N in PivNert, and you have all the other information about N. I'll answer that question in a minute. So PivNert this bad boy, and you get 0.0313 times 2 equals, you don't know this, R for atmospheres is 0.0821 times 298. Divide away from your variable, and you will get an N equal to a very small number. N is 0.00256 moles of H2O as a gas. Multiply that by 18, because that's how much water weighs. And you will get 0.046 grams of water as a gas. So, will any liquid be present? Yes. How much liquid? Well, you had 1.5. 0.046 has evaporated, and so you are left with 1.45-ish grams. Some other problems we did in class really quick, and then I'll get to the question about what I need to memorize. I wouldn't worry about this one with the